you organizers for inviting me to this event. Thank you very much for doing that. I'm really honored to be here in presence of this audience. And my talk today will be concerned with the CAV technologies, connected autonomous vehicles. And in particular, I'll be posting some challenges that we are currently facing that are concerned with the CAV sensors. So especially how to test the CAV sensors. What I want to emphasize that I'm here not only just to deliver a talk, but also to learn, because we are not having much experience in terms of the sensors and the development and testing. So I will be posting some questions at the end of my talk, and hopefully with some networking or during the panel, we'll be able to answer some of the questions. So maybe give a couple of the direction where we should navigate in order to find some solutions. So my talk today will be going through these items on the agenda. So I'll be giving a brief introduction into our company and what we're doing there. And then I will talk a couple of the brief words about the Assured CAV project, and then switch into our thought process, how we thought the connected autonomous vehicles should be tested. And then we'll give you a platform that we developed in order to execute this testing, which is called the DigiCAV. And finally, we'll focus on the challenges that we're currently facing regarding the CAV sensors. So I decided, instead of giving dry facts about HORIBA MIRA, to share with you with a video clip. And so what you're currently seeing it's the bird's view of our campus, which is located in Midlands in the United Kingdom. The clip I will be sharing with you will be a bit long, but I think it will give you a really good understanding of what we're doing there, what is the profile of our company, and justify to a certain degree why I'm here. Right. My apologies if you found the clip too long, but we are pretty proud what we're doing over there. Hence, I just want to share that with you. And let me now jump into the core part of my presentation. So in order to do that, I need to go back a bit of time to about 2015, 2016. And in the UK, at that moment, there were many statements in the press, and many automakers have promised that we will have fully functioning autonomous vehicles on our roads by 2020. For example, Volvo said that there will be about, I think, 200 Volvos XC90 driving around London and collecting data, fine-tuning this CAV technology. But we have a 2023, and I'm afraid we are still in the testing stage, right? It is not that no progress is done. It's actually huge progress has been done in that field. But it is just that sheer volume of testing create a so big obstacle that many of these automakers have to withdraw their promises and focus on that challenge of the testing. And this obstacle is also recognized by UK government, and they released a series of the programs and funding in order to support development and accelerate deployment of the CAV vehicles. One of the flagship projects was Assured CAV project, which HORIBA MIRA is part of it, and HORIBA MIRA offered the facilities that are existing facilities on the site, but also new facilities have been created in order to create a dedicated environment to test CAV technologies. So over here we can see many components on our site, and that includes the high-speed and urban and automated CAV parking, dedicated 4G, 5G infrastructure, robotic targets that allows you to run some dummies in front of the vehicles, dedicated public roads in order to carry out some tests in public. But what I like to focus in particular, it's a platform that is able to execute scenarios in the mixed reality way. And that platform is called the DigiCAV platform, and it sits under the umbrella of the Assured CAV. So what is DigiCAV? DigiCAV, it's a distributed and modular everything in the simulation loop platform. So it allows to combine both simulated and real actors to be executed within the same scenario context. So with that, we can accelerate deployment and accelerate also development of the new functions because we can test them on many different levels of their maturity. So this mixed reality aspect is really a USP of the DigiCAV. Normally platforms are allowing to run a real-time cost simulation that combines actors on the proving grounds, simulated actors in systems like CAV simulators, and DigiCAV is able to do that. So how this was done, in order to explain you how that was done, I need to take you a couple of the years back, and actually almost a decade back into the year 2010-2013, where DigiCAV has its roots. So it started with a cloud-based traffic management system, and that evolved through some research, and in particular PhD research, into cooperative driving platform. And at that stage, you already can see that we have a robotic cars driving around the circuit, but they are already mixed with the simulated one. So they're interacting and following cooperative platooning and merging together into that simple circuit. So that concept got a recognition within the company, and so they decided to replace some of these robotic platforms, robotic cars with actual car. So that when the network-guided vehicle has been introduced into DigiCAV, and the momentum was there, and at that moment, Innovate UK, so it's a part of the UK government, decided that it would be great if we can scale up this into a feasibility study. So that created a project that lasts, I think, for 2 years and project was successful, and many demonstrations has been done, also to not only to the stakeholders, but also to relatives. So you can see over here on that picture over there, there is Prince Williams actually entering that car, and that car will be later on driving around the proving ground. At some point in that story of the DigiCAV, my person arrived. So at around 2019 2019 and 2021, my story entwined with the story of DigiCAV. I will tell you a bit later about that. And finally, around 2021, the DigiCAV becomes a part of that Assured CAV project. So now, once you have an idea how DigiCAV evolved over the years, I'd like to also bring you into the thought process that was behind creation of the DigiCAV. So before I jump into that, I need to just do a very quick recap for those who are not aware about the CAV technologies. So if you're aware of that, you know that the CAV autonomous vehicles are equipped with a suite of the sensors. We will have a radar, LiDAR, cameras, different types of the radars, ultrasonic sensors. So this is just a certain set of the functions that are enabled by these sensors. And sensors for a CAV are absolutely critical. Without the sensors, there will be no CAV. So they are really, really important, because with them, CAV can interpret the scene around, and therefore execute some idea where to go. So what was our thought process about how these cars will be tested? So we like to employ some of our experiences in terms of the testing cars. So we thought that connected autonomous vehicles will have certain subsystems. So one of the first of the subsystems is situation awareness. So that subsystem will take the feed from the sensors and then process it, creating a scene interpretation, image of the scene. So that will be then fed into the path planning system that will create a trajectory. Quite often that trajectory will be adjusted, hence to the information coming from the infrastructure or from other actors on the roads. And finally, once the trajectory is confirmed, we can send that to the actuation system, and then the vehicle will move. So this is very likely how the whole system will work together. And now we need to think outside of the car and how this vehicle will be interacting with the driving environment. So first of all, this environment needs to provide a stimulants for our sensors. Secondly, we need to have a way to communicate with the other actors or infrastructure over there. And finally, our car, under the test, must somehow interact with that environment. So make sure that some other actors will be interacting to our motion as well. Now, so this concept assumes that we already have the fully functioning autonomous vehicles. But in fact, that is rarely a case. Because quite often, what customers want to test is some certain functions of this particular subsystems. So we should be able also to create a testing environment in order to test a situation of awareness system. So this testing environment needs to provide the feeds, simulated sensor data, so the situation awareness can be evaluated against the ground truth. Similar can be done with the path planning. Path planning also may take into account what is currently happening. So we need to provide a certain situation image, and then again be able to provide the ways so we can evaluate the trajectory against some benchmark and decide whether that benchmark is met with this and satisfies conditions. Or instead of just testing one particular function in standalone way, we can combine some subsystems together. So at every stage of the development, we would very likely be asked to test some particular subsystems or combine subsystems together. So now, when you also add another part to that complexity of the testing, that each of these subsystems could be a different level of development. Some of them may be in form of the models. Some of them may be in form of the software, application or services that we need to include. Some of them may be mature enough to be uploaded to the ECU. Or it could be that we have to use partially assembled car that is connected to the Dyno, or fully functioning autonomous vehicles. So each of these subsystems could be in a different stage of the maturity. So our test driving platform should be able to account for this as well. And along with the progress in development of each of these particular subsystems, some of these functions may be transferred into a vehicle. So incrementally, these functions will be then transformed into a vehicle, and finally, at some point, the whole vehicle will be tested in our platform. So that was the thought process behind the creation of the DigiGov. We have to account for all of these subsystems, be able to test them in the standalone fashion, combine them together, and also account for different level of development. So the result was a platform. We call it a DigiCAV, which stands for a Digital CAV Proving Ground System. And this system is not a simulation platform, right? I want to clarify that. It's a co-simulation platform. This system facilitates simulation and enables to mix different actors, physical or simulated, in different level of maturity. So we develop different interfaces in order to enable to include models, to include the software, so you can communicate with the TCP or UDP, CAN systems. So we have interfaces also to the infrastructure as well. So with set of these interfaces and with this concept, we are ready to actually test any part of the CAV technology. And this testing was developed with this particular approach that at every level, you can carry out the test. And thanks to that, you can detect some mistakes you may have done at the modeling level. So instead of waiting until the car is fully assembled, you already can detect some mistakes at early stage of development. Because DigiCAV is not a simulator, it requires certain input into it, and that is a scenario. So we decided to follow the concept of the scenario-based testing. However, this concept itself at that moment was not really well addressed. Because if you think just about the real-world testing and scenario-based testing, quite quickly you realize that it's not really feasible. The reason is, it is because of the vast scale of the parameters you need to consider. Even for that particular one scenario, there might be parameters that will describe our road geometry, the width of the lane, the width of the roads, the type of the roads, roundabout, two-way roads. Then you can have some additional information about the markings. Then we add a bit more complexity with traffic lights or the buildings. Some of these buildings may obstruct field of view for certain actors over there. And then actors in the scene. Some of these actors we like to be able to simulate. Some of them will be great to have a real, but the problem immediately arrives at that moment, how to reproduce that particular scenario many times and just vary some particular condition of that scene, let's say lighting, weather. And then finally, a bit more complexity, we could have a communication between the actors, and we need to account for that as well. So very quickly you can see that the amount of the parameters that are needed to be considered is really huge. Hence, there was a consensus amongst the stakeholders that the real-world testing is not really the way to go forward. Hence, there was a shift at that moment to move into a virtual testing. And that need created many solutions to support the virtual CAV testing. Some of them were developed from scratch. Some of them were developed on the already existing solutions. So this particular slide includes some of the tools I encountered, but there's definitely dozens, if not hundreds, of these solutions that were developed in every university, every research institute for their particular use case. Also, there were a number of tools that were introduced into that pool, not to provide a CAV simulator, but just to enrich the simulation. So that might be an example of the Sumo, a traffic simulator. Some of these tools over here were developed in order to make sure that we can move some scenarios between these software, and that is the Open Drive standard that tells you how to describe the road network. So this resulted in many of these AV, autonomous vehicle simulators, be already on the market. And in the current state, they can provide really fantastic environment, really rich in visuals. So you can very quickly create a car there, attach some sensors. Over here we have a suite of the sensors with the video cameras attached with the different angles, LiDARs as well. And furthermore, we have a full control over that environment. We can change the lighting condition, the weather conditions. We can inject additional actors at any position we want. We can provide them with some certain trajectory. So this enabled developers to create lots of functions and test them in the different configurations. We also utilize that concept. So what we've done is just take our map, so you can quickly take your map, create digital twin of it, import that map into that software, into that simulator, and attach some sensors. Some of these sensors are mimicking real sensors, like RGB cameras or LiDAR, but some of them are just the software constructs, like an instant segmentation camera. Taking CAL as an example, I'd like to show you how very easy you can just create a sensor over there and attach to a vehicle. So this is just a part of the code that the top one will use a blueprint for a LiDAR. And then you can define some certain parameters for that LiDAR. The bottom part of that code creates a radar. And then you can very quickly attach that to your vehicle and release it. So fantastic. And you can see the sensor suite for the car is quite extensive. And other simulators also have this quite extensive list of the sensors. Some of them are software constructs that combine some information and process it and giving you with some feeds. But I'd like to highlight that at this moment, we can do it in a very simplistic way, but there's not many actually studies to assess how well these models are actually representing the real devices. Right? So this particular blueprint allows you to create something that mimics a rotating LiDAR. What about the flash LiDAR? Right? Then you very likely need to create your own construct in order to include something like that into the simulation. At that time, when these simulators were developed, I was actually working not at the HORIBA MIRA, but at Dyno for the university. And we also wanted to address that problem of the driving environment for CAV. But our take was slightly different, because myself and my colleagues were also interested in the human factors. So that's the reason we wanted to have something in the loop that allows us to include a driver. Right? So what we created, it's an immersive vehicle visuality testbed that contains a 6-degree of motion platform, VR headsets, and also steering wheels with the haptic feedback, and etc. And also supplementary sensors. The reason I'm saying about that, because I always get the question why I'm using the screens, why having a VR headset on the head, because on the daily basis, we tend to use the screens because it's much more efficient. So the concept maybe is not very unique. There's plenty of these driving simulators around, but this particular one has one special USP. It was portable. So maybe it didn't offer capabilities of these full-scale simulators in terms of the range of the motion and etc., but it was portable. So we could take that to any place we want and integrate that with the ecosystem of the particular CAV testing platform. And that uniqueness of that solution allow us to win some funding from the Royal Society and Royal Academy of Engineering. And we took that simulator and moved to the HORIBA MIRA. And so this is the moment when I started to be connecting with HORIBA MIRA. So we've done some work, so you can see me over there, trying to integrate this simulator with the ecosystem. So we've done that in order to create a platform that will have a human in the loop. So additional different actor, right, to the DigiCAV platform. So let's summarize at this moment in terms of what we have. At this moment, DigiCAV is able then to carry out all of these different simulations, model in the loop, simulate software in the loop, hardware in the loop, and vehicle in the loop, thanks to advances in terms of the CAV simulators. Because what DigiCAV cannot do is, like I said, simulate. It's not a simulator. It's a real-time platform enabling co-simulation and enabling cooperation between all of these actors that are within the one scenario context. So in order to execute that in a reproducible way, we need to have an input from the scenarios. So hence, we were really glad with the advances in CAV simulators, because we can use that as an input to create a particular scenario. So what this platform can do? It can create and configure a scenario. It can simulate and control smart actors, although that word simulation refers to very low modality models of vehicles. It can control physical actors on the proving ground, and that control is really precise. And this control is currently with our proving ground, it's within the 20 centimeters precision. It can communicate and simulate infrastructure. It can communicate with infrastructure that we have on the proving ground. It can collect data, visualize this testing scenario, and also enabling inclusion of different models, different software, different interfaces into whole platform. So this is the overview of the DigiCAV structure. What I like to highlight in this particular slide, it's not the complexity of it, but one also very important concept of DigiCAV. DigiCAV is a vehicle agnostic. So it means it doesn't care what vehicle we including into our platform. Because this is really important when you think about the customers trying to test their cars. They really don't want to reveal all of these secrets, all of these algorithms. All what we need is actually how to drive the car. So DigiCAV is vehicle agnostic, but we're creating a small interface that allows us to control the car. But beyond that, we're not really interested what is inside the car. So let me show you a small demo how DigiCAV is actually working. And for this particular demo, we'll utilize our proving ground. So this is our proving ground. So we have a digital twin of that. So we have 4 screens over here. So the top screen of that demo, this is CALLA simulator. So this provides some visuals to us. Also, you can populate that CALLA simulator with some actors that will be then visible by within the DigiCAV. Over here, this particular screen will demonstrate you that we're not using just the simulated actors. There will be a real human-in-the-loop simulation. That's me, that's the proof. So this is myself recording this particular scenario. So we just use our desktop simulator in order to do that. Then we have a top screen over there that creates a scene visualization. It's very, very helpful because it's minimalistic, so you can know where all the actors are. And also within that scene visualization, I just attach a sensor, which is a LiDAR, to that car I will be driving, and exaggerated a bit with its parameters in order to be visible. And this screen over here represents a DigiCAV. So this is very old and now already obsolete visualization of the DigiCAV, because the DigiCAV is actually just a code. It's just a code. So in this particular case, I just want to highlight that DigiCAV will be controlling all of these actors. It will be able to recognize their position and then execute certain scenario. So in this particular scenario, we have myself driving on the driving simulator, but also we'll have 2 platoons of the cars there. So at the top, especially on that screen, you can see there's 2 cars. So there's 1 platoon of the 2 cars, and then another platoon of the 5 cars that are in front of me. So now this simulation is being executed. So they're following a certain trajectory, but the concept behind this particular scenario is to execute cooperative platooning. So these 2 platoons should seamlessly merge together and follow to the final destination. However, there's no problem at all that we take some of these cars from both of the platoons and replace them with the actual physical cars on the proving ground. So over here, you can see it is recording of the same scenario, but instead of having all of these cars simulated, this time we added real physical cars that are driving on the proving ground. And these cars can see the simulated cars, and both simulated cars can see the real cars. So if I carry on with that particular scenario, you can see that I'll be then trying to catch up with that platoon. Because I'm a very impatient driver, I'll be trying to overtake every car in that platoon on the bend, which can be done in the safety of the proving ground, actually. So this demo hopefully gave you a glimpse what DigiCAV is capable of. And on this screen, I just want to highlight what are the interfaces and what can be connected to the DigiCAV platform. So we can communicate with the models, developing the MATLAB, MathWorks systems. We can execute hardware-in-the-loop simulation as well. We can connect to the laboratory equipment, Dynos. We can control physical actors, or we can control also the actors that are kind of platforms on top of which you can attach some dummies and execute some critical scenarios. However, at that point, we realized that all that shift towards the visual world created some challenges for us. And this challenge is related with the sensors, and in particular, how to stimulate the real sensors. Right? So most of these CAV simulators enabling us to create these software constructs and software representations of the sensors. But at some point, very likely, all of these components will have to be tested in the real world. And this is a problem that we're currently facing. How, with a data that is generated in the visual world, how we be able to stimulate these real sensors? And how generate these stimulants for a wide range of the operation of this particular sensor, or even beyond, because we want to assess how they are working on the spectrum of the operation conditions. What about the noise? We know that every measurement is, in the real world, is contaminated, corrupted with the noise to the certain degree. So how we find the magnitude of the noise that we should use in that, whether we will do it on the simulation level, visual world level, or maybe we introduce into some laboratory equipment that will generate this noise for us. How to ensure also that the approach we're developing will be valid for the products that are currently on the market. I already mentioned that the color allows you to create a LiDAR model, but it is a rotating LiDAR. What about the flash LiDAR, if someone decided to use the flash LiDAR? What metrics we actually should use in order to assess that performance? So whether we should just use the standard root mean square or something, whether we should combine some metrics for multiple of the sensors. So lots of the questions are appearing. And the one that I'm actually very interested in and already started to do some research in that field is, what about the sensor deterioration? Because so far, most of these functions of the CAV are tested in such a way that the sensors are treated in the binary way. Working, not working. But actually, they might be, let's say, camera can have some dirt on the lenses and how that will deteriorate its performance, and then how that performance will affect some functions that are associated with the camera. So as you can see, we are facing a lot of the challenges, and in particular, challenges about how to deal with that problem of moving from the virtual world now back to the real world. I thought maybe some inspiration might be the way we stimulate the human sensors. So over here, it's a clip I recorded some time ago, where I'm I'm using that driving simulator to have a bit of fun and driving, and don't remember what the game was. But what I want to point out here is the way our sensors are stimulated here. So the sensors of the human driver on the simulator are stimulated in such a way it feels as a realistic experience. So the presentation of this visual, acoustic, vestibular, and haptic information is done such a way that we actually perceiving being in actual car. And what enabled us to do that? So first of all, advancing the game engines, so they can now create a fantastic visuals. So we can now assess, we can now have a almost photorealistic view on the scene. Then VR headset will help you to assess the distance to other objects, sink into that simulation much quicker. Haptic information coming from the steering wheel, from the pedals as well, because they are being adjusted so you can feel the way the car is being driven. Binaural sound will tell you if someone is behind you, and you can already also assess the distance to that object, making the sound. And motion cue algorithms. So all of these displacement from, acceleration, angular acceleration, linear velocity, and angular velocity, all of these parameters, all of these values are not being translated into one-to-one into that motion platform. Actually, our inner eye is being tricked, and is being tricked with the help of the motion cue algorithms. So these motion cue algorithms takes these values and translate them in such a way that we having this sensation of acceleration, we having that sensation of braking. Although I need to admit it takes a bit of time to tune that platform. But I thought maybe this could be an inspiration how to stimulate, and whether these ideas can be also used to stimulate the CAV sensors, because actually both human and CAV sensors are being used for the same purpose if in the context of autonomous driving. And in fact, some of the work is already been done by a colleagues in HORIBA, and actually in Germany division of the HORIBA. So they come up with some idea how to stimulate the LiDAR. The idea is pretty simple, which contains a system called the LTS, which is the LiDAR test system. And the way it's being done, that actual LiDAR that is mounted on the car is being blocked from sending the lasers. Instead, that moment is being used as a trigger and being fed to that LTS system to generate laser beams that are being adjusted to reflect what is happening on the screen. So the laser beams being adjusted, time delayed, specifically to represent a distance, and these lasers beams are being reflected from the screen and then sensed by the LiDAR sensing component. You can see they already done some tests with this LiDAR stimulation, and so far they are quite successful on that front. So you can see a vehicle that is actually on the chassis Dyno. So the vehicle is being, as you can notice, being driven and speed up about 30 miles per hour. At top of that rig, you can see two projectors. So one projector presents the visuals on the screen, but the second projector is that LTS that will be sending the laser beams that will be then reflected from the screen and then sensed by the car. So I think at that moment we should be approaching the car that is stationed on the lane, and the test over here is the test of the automatic emergency braking. So now the system on actual car should be able to detect this visual construct and stop. As you can see, these are just a result they recorded, and so far it looks that across the many runs, they can reproduce these results quite good. Although this is still work under development, and lots of the work must be done in order to ensure that this concept is valid for many other products as well. So with that, I'd like to finish my talk. So thank you very much for listening to my talk, and hopefully I can answer some questions that are concerning this particular topic, or maybe some questions that are outside of that topic. I will try to answer them as well if possible. And I'm looking forward also to network with you, because you're the expert in the field in terms of the sensors. Hence, any advice, any direction is really valuable for us. So again, thank you very much. If you wish to contact me outside this event, please follow these details on the screen. Thank you.